In this section, we're going to be taking a look at some notation that makes it convenient to work with systems. It's called matrix algebra. This is going to replace this replaces section 7.2. If you've had linear algebra before, most of this will be review. The main thing for us is we're going to be only working with systems of 2 or 3 equations. Okay, but mostly it'll be 2. Every once in a while I may mention a system of 3, but it's really a system of 2 equations that we're going to be working with. And so that simplifies everything by quite a bit. And so here's our key definition that'll hopefully make this a little clearer. If I have 2 equations, ax plus by equals e, cx plus dy equals f, then this system of equations is completely the same, or completely equivalent to the following notation. Whoops, a, b, c, d, x, y equals e, f. Okay, so these two things are exactly the same. This is exactly the same as this. Okay, and so this is called a matrix vector form. You see here these two things are vectors, but remember we're going to be writing our vectors now in column form. And so this thing right here is a matrix. Okay, and in fact it's called a coefficient matrix because we're pulling the coefficients out of our equations and listing them there. So just to be I said I wasn't going to do 3 dimensions very often, but let's just go ahead and do it now just so you can see how this works. So with the larger system of equations, I might have a11 x1 plus a12 x2 plus a13 x3 equals b1, a21 x2 plus x2, oops, sorry, moving around on me, x2 plus a23 x3 equals b2, and a31 x1, that's an x1 there, I'm trying to go fast, a32 x2 plus a33 x3 equals b3. So this is completely equivalent to the matrix vector form a11, a12, a13, a21, a22, a23, a31, a32, a33 times x1, x2, x3 equals b1, b2, b3. Okay, and so you can even think of this as a way of defining this, right? So if I want to compute what this is, I would go through and compute my system of equations. Very good. Okay, now just to let you know, if we refer to an entry of the matrix, an entry of matrix A, say the ij entry, the ij entry is the entry found using the ith row and jth column, and it's always in this order, always in row column order. Okay, so let's do an example. 1, 3, 2, 4. So what entry is 3? 3 is in the 1, 2 position. Right? It's in row 1, column 2. Row 1, column 2. Very good. All right. So now let's do one more example. Suppose I have 3x minus 2y equals 4, and x plus y equals minus 1. Go ahead and rewrite that in terms of matrix vector form. You should pause the video here and do it, and then I'm going to continue. We'll say, okay, so continuing, that is 3 minus 2, 1, 1 times xy equals 4 minus 1. Did you get that? Excellent. All right, similarly, so that's one example. Another example, suppose I've got 3 minus 2, 1, 1, and I want to multiply that by 1, 2. What answer do we get? Go ahead and press pause. Okay, let's go ahead and fill it out here. This is 3 times 1 plus minus 2 times 2. And then this one is going to be 1 times 1 plus 1 times 2. Right, so that's going to be 3 minus 4 is minus 1. 1 plus 2 is 3. Good. All right. And so that's what matrix vector notation looks like. The other thing I want to define, definition, and this we looked at in Calc 3, the determinant of a matrix A. Oh, let me say A, B, C, D. And so our notation is we could either write the determinant, or we can use this just straight lines. And you might remember from Calc 3 that it's AD minus BC, right? You take the multiplication of this way, and then you subtract this way. Good. All right. Similarly, we could define the determinant of a 3 by 3. You'll remember that from a cross product, but we won't do that right now because we will only very rarely take the determinant of a 3 by 3. One other thing I did want to define before we go, there's a couple things to define. The transpose of A. So the transpose, well, let me rewrite it. The transpose of A is denoted with A with a capital T, and the way you write it is the main diagonal, well, maybe a different way to say this is this first column becomes the first row, and then the second column becomes the second row. And so you'll notice that along the diagonal nothing changed from here, but these elements flipped. Okay, and so that is the transpose of a matrix. Good. Just a couple other pieces of notation. How about scalar multiplication? So if I take C times A, B, D, E, sorry about that, that's going to be AC, BC, DC, EC, just like you would expect. Similarly, one more thing to define, matrix multiplication. We won't be doing this very often, but it may come in helpful later. If I take a matrix A, B, C, D, and I multiply it by E, F, G, H, the way that's defined is it's a new matrix, and the first column is A, B, C, D times the first column of your matrix, and then the second column is the second. You multiply this matrix times your second column. Let's see, that was FH. Okay, so this matrix times this matrix, it does depend on the order, right? Because the first column is going to be when I multiply this times that. Second column is when I multiply the matrix times the second column, right? So then I just have to compute those, and if we could fill those in if you like. It's going to be AE plus BF, CE plus DF, AF plus BH, CF plus DH. Okay, like I said, we're not going to do this very often, but it's good to know what the definitions are when we run across them. One last thing before I close this video, and that is the identity. Oh, maybe I should wait for the identity matrix for the next video. Okay, so the next video we're going to be picking up on page 3 of the notes in the identity. See you then.